the SCR, when you hook it up in an AC circuit, it's the way that it looks is kind of like this. I want to show you. This is an AC source, and if I take a point like this, and I come along and I put a switch in, and then I put a load in, like that, and just a maintained switch like this. This is actually kind of similar to what an SCR does. We would look at this and we would say, if we came here, we said this is 120 volts AC, and we came along and we looked at this circuit in the condition that it is right now, we would take a voltmeter and we would say the voltage across the switch is 120 volts. And the voltage across the load is 0 volts. And that's because there's no current flowing, right? This is the return path to my source, okay? 120 volts across the open switch, 0 volts across the load. Now, if we came to this switch and we close the switch like that, this value should go to 0 volts, and this value should go pretty much to 120 volts across our load. And this is the way our typical circuit, an AC circuit, would work with just a switch in it. The only difference is that how do we get the switch from here to here? Well, this takes a physical action, a physical push on the switch. And the switches that we use, particularly just wall-mounted switches that we use for lights and things, you know, it's just a one push thing and it closes. So what would be the difference then if we took this device and replaced it with an SCR? Now the SCR, to begin with, does something a little bit different than a regular switch would. Now the first thing that it does is kind of the same. When we look at this and we put this in, we see that that's our gate there, anode, cathode. Guess what? If we just threw the switch, turned this 120 volt source on, no gate pulse, then what we would really see is we would see 120 volts across that SCR, because it would be like an open switch, and we would see 0 volts across the load. Now, what would happen if we were to take this and apply to the gate a trigger pulse? And what I want to show you is this. Let's say that this is the AC waveform, okay? Looks like this. This is our 120 volts AC input, okay? Input. Now, I would call this point 0 degrees. I would call this point 180 degrees, and this point 360 degrees for one complete cycle. Now, we know that an SCR can only conduct from A to K. And so what I want to do is I'm going to say this. How about if I apply a trigger pulse right there at 0 degrees? Well, here's what would happen. That would mean that the SCR would be closing. And so that would mean that this voltage would drop down to some very small voltage. I'm just going to put here VF, whatever that forward voltage drop is. And once we're talking about 120 volts, this is kind of negligible. We don't worry too much about that value. Basically, we just say the switch would close. As soon as we trigger this, the switch closes. And that means that I would then have, roughly speaking, about 120 volts across the load. But what's important to understand is if I were to put a scope across the SCR and 1 across the load, what would I see in this circuit? Because remember, it will conduct now from 0 all the way to here. What's going to happen when all of a sudden this becomes positive and this becomes negative? As we go into this negative alternation down here, now we're going to be pushing from this side. What does an SCR do when it's reverse biased? It blocks up to a very high level. And so that means that we can only ever conduct with an SCR during the positive alternation. It's the only place that we have the possibility of conducting in the SCR. And so during this alternation, the SCR always blocks in the negative alternation, always blocks. So the only thing that we're going to do, the only part of the AC waveform that the SCR can control is the first, or what we call the positive alternation, generally speaking. Okay. Now, what I want to do is I want to show you the waveforms so that you can see what they look like. And so I'm going to show it like this. This will be what the scope will look like if I place a channel across the SCR. And this is what the scope will look like if I place a channel across the load. So I'm going to put my probes on here like this. Okay. And I'm going to put my other channel over here. Okay, so channel A and channel B. And let's see what happens. SCR is A, load is B. So as you can see, we're applying voltage against the SCR, but we trigger it almost instantly. So that means that the SCR really does this. It might block like this. It starts to block a little bit, and then it just goes like this. Now, when the SCR is closed, we don't see any waveform because what's happening is it's allowing conduction. And so we don't actually see the waveform because it's allowing the conduction to happen. Now, when we get to the end of this alternation, well, how does the SCR shut off? And here's something really interesting. How does the SCR actually open when we know that we actually have to get below a holding current level for it to open? So we look at it and we go, well, guess what? If we trigger it here, it closes. It conducts. When it gets to this end, as the voltage falls, so does the current that's flowing from anode to cathode. And so it just naturally shuts off. It falls below the current, the holding current level, and shuts off. And so in this instance, this is actually called, what happens at the end of this point right here, please make a note of this, this is called natural commutation. In other words, you know what? At the end of the first alternation, the SCR automatically shuts off because the line voltage falls to 0 because it's an AC voltage. And so natural commutation, also called sometimes line commutation. So a little bit different than in DC where we had to force it off. Okay, natural or line commutation. Now, let's look at the voltage waveform that we see. So we're now to the end of the first alternation. The SCR basically conducted, so we don't see any blocking waveform across there. What's it going to do when it gets here? Well, now the AC supply is reversed, and so the SCR is going to experience a negative peak of voltage that rises and falls, and it's going to look like this on the scope. Okay, that's what you're going to see on the scope. So the SCR conducts here, shuts off at the end of the alternation naturally, and then it blocks till the end of the cycle. So we're at the end of the second alternation. Now, what does the load look like during this period of time? Well, it looks like this. We're going to start down here, And we're going to say, you know what? If the SCR is closed, the switch is closed, as the AC rises, my load is going to experience voltage like this. And then that voltage is going to fall as we get to the end of the alternation. The load voltage will come to 0. Now, if the SCR is blocking, then there's absolutely no current going through either the SCR or the load. And so that means that my load voltage will look like this during the second alternation. Now, what I want you to understand is, what does this look an awful lot like? Well, this looks like a half-wave single-phase rectifier. Now, we could have developed a waveform like this by just putting in a simple diode in series with the load, and we would have got this waveform. So, what is the advantage then to using an SCR? So let's take a look at what that advantage will be. So what I want to do is I just want to summarize briefly. If we take, I just want to look at the waveform across the SCR. If we take an SCR that is connected in an AC circuit and we look at no trigger pulse, then the waveform across the SCR will look like this. Okay, that's with no trigger pulse. If we give it a trigger pulse, okay, and we give it that trigger pulse at 0 degrees, then the SCR looks like this. And it blocks the second alternation. So now, instead of having blocking and blocking, we have conducting and blocking. Now, what about this? What if I actually set up a special circuit, a trigger circuit, and I gave the trigger pulse at 90 degrees, And so I'm going to draw that waveform right here. Now, this is the SCR we're talking about, right? Now, that means that the trigger pulse, I'm going to put it on this line. Here's my whole cycle. This is 180. This is 90. So that means this is going to be where I am going to fire the SCR. So watch carefully as I develop the waveform that will appear across the SCR. And it looks like this. The voltage will rise, and the SCR will be blocking because it has not been fired. Now, when we get to the top, this is where we go, okay, now's the time. Bang, in goes a shot of current into the gate. It fires it, it latches, it turns that SCR on, and watch what happens to the waveform of voltage across the SCR. It goes like this, and then it crosses here with just that minimal voltage on. And when it gets very close to the end, the current gets too low and it drops like that. Okay, it drops off, and it basically, this point right here is natural commutation. Natural commutation. Now, what does it do over in the next alternation? Well, it's going to do this. It's going to block. Okay. Now, on the same graph, I'm going to show you what will happen to the load voltage. I'm just going to show you the load voltage in red. If we do not trigger the pulse, give a trigger pulse to the gate, then the load voltage will be just 0, and it'll look like this. Now, if we don't turn the SCR on, then our load is 0. Now, because the SCR never basically turns on in this side, the load is always 0 over there, in this case, because it's kind of like a half-wave controllable rectifier. So there's your load voltage, nothing, straight line. You see the full AC waveform across the SCR, and you see nothing for the load. Now, what will the load voltage look like here? Well, while the SCR is conducting, the load voltage will do this. and we'll get almost that whole alternation. And because the SCR only conducts one direction, it always blocks this way, the load is at 0 during this alternation. There's your half-wave rectifier. Now, what happens over here? Take a close look. As the SCR is blocking for the first 90 degrees, we have no load voltage. However, when the SCR fires and closes, the SCR voltage drops to almost 0, and the load voltage rises to pretty much up there. And it will now conduct from 90 degrees until 180 degrees about. That's the point where it will shut off. Now, while the SCR is blocking the negative alternation, the load voltage will be 0. So what's the difference here? Look at how much voltage here we have for the load. Here, this is 0 volts, right? Now, we know that a half-wave rectifier is E line times 0.45. That's how much voltage we would have here. Whatever the line voltage is times 0.45, one full ripple. How much of a ripple do we have here? Well, this one is blocking for exactly the first 90 degrees. Then it's conducting for exactly 90 degrees. And then it's blocking for the other alternation. It looks just like this, except this is split in half. So in fact, at this point, what we have is a quarter wave rectifier. And you could actually say E line times 0.225. Now that only works at basically 0 degrees or 90 degrees. You can use that. Here you can say it's a half wave. Here you can say it's a quarter wave. Now because this is a sinusoidal waveform, anything in between, any angle in between that you fire, you're going to have to use a special formula to find the amount of average voltage. But if you fire at 90 degrees, it's E line times 0.225. If you fire at 0 degrees, it's E line times 0.45, just the same as if it was a diode. But now because we have an SCR, we can actually delay the firing angle halfway through the alternation. In fact, we can delay it all the way to the end with a special trigger circuit. Now, the first triggering circuit that we're going to talk about is going to be the resistance-only triggering circuit, and it will only be able to trigger from 0 to 90 degrees. Now, before we finish, before we get into talking about the resistance-only trigger circuit, there's just one more thing that I'd like to show you. Seeing as the SCR only controls one alternation, and then it always blocks for the second alternation, I want to go into a little bit of detail about that alternation and let's see what it looks like. If I draw a line and I say here's one alternation, okay? Now, from our studies, we should remember that this is equivalent to 180 degrees, okay? So one alternation, 180 electrical degrees. And so this is really the alternation that we have the option of controlling. Now, if we fire at 0 degrees, then the load will see the entire alternation. If we fire at 90 degrees, then it will only see half of that alternation. If we fire here sooner at say 45 degrees, it will see 3/4 of that, and so on, depending where we fire. Now, there's two separate terms here. I'm going to just choose an angle here at some point, put it right here. Let's say that this is my firing angle. Okay, now the firing angle is the angle in degrees. Okay, it's the angle in degrees where we apply the trigger pulse to the gate and the SCR turns on. That is the angle. And so what we could say is everything up to this point is blocking. Okay, we're blocking. The SCR is not allowing current flow during that period of time. And everything that happens after that, until the end of the alternation, we would call conducting. Conducting. And so, seeing as an SCR is really only capable of managing one alternation, here's what we can say. If you take the firing angle plus the conduction angle, it always equals 180 degrees. So in other words, if your firing angle is 90, then your conducting angle is 90, and the two of them equal 180. If your firing angle is 30 and your conducting angle is 150, 180 degrees. What do you do if your conducting angle is 25 degrees? Oh, let me see. You want to know the firing angle. So you go 180 minus 25. That means your firing angle must be 155 degrees. So you can always figure this out and work it back and forth. Realize you're managing one complete alternation that is 180 degrees in length, and your firing plus conduction is always equals that entire alternation. So what we need to do then is we're going to have some circuits that will allow us to send that trigger pulse to the gate at any point from 0 to 180 degrees. Now, the firing angle can be controlled by a couple of different trigger circuits, okay? Firing angle controlled by, okay? And the first way is what we call resistance only. And the second way is resistance and capacitance. Okay, so we've got two different circuits. One will be resistance only, second, resistance and capacitance. Now, what's the difference between the two? Well, the first one, you can actually only fire the SCR between 0 and 90 degrees. So you can only have firing angles up to here. With resistance only, you are limited to 90 degrees. If you have resistance and capacitance, then you can go anywhere from 0 to 180 degrees. And really the only difference is it's a little bit more elaborate, the circuit, takes some extra components. So when it comes to some types of equipment that use this for voltage control, the ones that give you the full phase control, you can basically manage that alternation all the way to the end, are usually a little more expensive. And that, that's typically what happens there. So the first one we're going to look at is going to be the resistance only. Now I'm going to draw a circuit, a very typical circuit with the SCR in it, and it will look like this. This is an SCR used essentially as a half-wave rectifier. Half-wave rectifier. And let me show it to you like this. I'm going to start with line 1 and neutral over here. This is just a single phase, okay? I'm going to come down here, and at this point, I'm going to put a load resistor. Now, this load will be in series with an SCR. So this is going to be the switch. There's the cathode, and it's attached to neutral up there. And this is going to be the gate right here. Now, this line right here from line to neutral, I would call this the load branch. The load branch. Now this is a parallel circuit. We're also going to take from line 1 and we're going to feed into this resistor. I'm going to make this a variable resistor so that we can see what will happen as we manage the resistance in the circuit. Now, remember when we were talking about essentially the characteristics of the SCR, we said that current always has to go from A to K, and that current in the gate has to go from G to K. Okay, that's a necessary thing, A to K and G to K. And so what I want to show you is this. If you take an AC waveform of voltage like this, and you say, here is, if I go into this one here, I say I've got a rising voltage here, that means I'm going to apply some positive potential to this point. Now, nothing's going to happen until I actually, fire the SCR, but I've also got, there's going to be current that will come down, it will flow through this, and it would flow, if I connect this straight to the gate, during this alternation, the current will flow into the gate, to the cathode, and up to that line up there. But let me show you what would happen if I don't take some special measures. When this alternation becomes negative, it will now start to push from this side. Now, the cathode has a nice, strong blocking voltage, cathode to anode. So the SCR is fine. It just shuts off and blocks. The gate can only handle about 5 volts of reverse voltage. So what that means is, as soon as we reach 5 volts, so that means, right about here, by the time we get to that 5 volts going negative, the gate can't handle it anymore, and the gate is not allowed to have current going this way, and so it literally blows the gate off of the SCR. And that's it, that's the end of your circuit. So how do we prevent that kind of damage from happening? Well, here's the thing. We put the resistor, and then we put in a diode right here, and we bias it in the same direction as the SCR. Now this is just a simple diode, okay? That's all it is. And it goes like this, and it ties to the gate. Now that means, we know that diodes only allow current in one way. And so what that means is this. Current will be flowing this way during this positive alternation, and when we go into the negative alternation, it would like to push current through the gate, but it would be blocked by this diode. And so the name of this diode is a gate protection diode. And it will not allow the reverse flow of current through the gate, thereby destroying the SCR. So very, very key element, very important component when we're building these circuits. Let's take a look. I want to see what the waveforms of voltage, how much voltage will we actually get for the load given different firing angles. And I want to show it to you like this. I'm just going to draw a few of these little angles. Okay, and we're just going to put a random sort of firing angle in, and we're going to look at what the waveform of voltage is like. And the reason I'm doing this is just for us to get an idea of what really happens. Okay, so now we're talking load voltage. So if I fire at 0 degrees and I want to look at 1 cycle, then I get a voltage like this. Okay, that's what I get if I fire at 0 degrees. What would I get if I fired at, let's say, 30 degrees? Well, I would see something that would look like this. The load will see no voltage while the SCR is blocking. And so what you're going to see is this little, kind of this nibble out of the front of that waveform. And then when it turns on, it goes straight up. And then you'll see the rest of it as if it was normal. And during the second alternation, of course, blocking. This is the voltage you would see at, let's say, 30 degrees. Now, what would it look like at 90 degrees? Well, it's going to block like this. Then it's going to go turn straight on. We're at 90 degrees, so now we're going to just see that last quarter there, and this will turn off like this. So what I want you to see, this would be 90 degrees firing angle. So the later that we fire, basically the lower our load voltage would be, because if you look at it, this one might be an average voltage of, say, about this much. Now this one would be just a little bit lower, like that, and this one would be down here. So the later that you fire the SCR, the lower the load voltage. And so I like to use this little, just a little sort of phrase that I use. Later is less for the load. Later is less for the load. So the later the firing angle, the lower the load voltage will actually be. And so what I want to show you is a formula that we can use to determine what the actual amount of load voltage is based on any given firing angle. So I'm going to clean this off here, and I'm going to show you the formula. Now this is a half-wave rectifier, and so what I'm going to do is the formula. This formula is specific for the half-wave. Okay, so this is the half-wave controllable rectifier. And the formula that I'm going to give you will tell you the voltage of the load for any given firing angle. And the formula actually looks like this. E average, which is the DC or the load voltage, is equal to E peak. Okay, so that's the ultimate height of the AC waveform. E peak times 1 plus the cosine of the firing angle, cosine of the firing angle, and that's all divided by 2 pi. Okay, so there's a formula. E average is equal to E peak times 1 plus the cosine of the firing angle divided by 2 pi. So I want to look at some of the values using the formula that we just talked about, and that formula again is E average is equal to 1 plus the cos of the firing angle divided by 2 pi. Okay, gives us our average voltage. I'd like you to work it out for these 3 examples right here. Now, just to give you a couple of sort of goalpost marks, if I built a circuit with just a diode in it, we know that the form factor for a half-wave rectifier like this one that I've shown is E line times 0.45. And so we would go 120 times 0.45 equals 54 volts. So I know that if I fire at 0 degrees in this circuit, I should get about 54 volts. Let's go ahead and start with this one, maybe this 15 degrees down here, 15 degrees. So what I'd like you to do is put in 1 plus the cosine, 15 degrees, divided by 2 pi, and I'll give you a second to run that through. Order of operations is important. Make sure you do this part first, then divide by 2 pi, then multiply by, oh, sorry, I need to put in here, this is all multiplied by E peak, okay? So you have to multiply by E peak, and then that'll give you the average voltage. So what I see is for this one at 15 degrees, 53.2 volts. So that means for 15 degrees of delay before I fire it, I literally only lost 0.8 of a volt, 0.8 of a volt of my average voltage. That's all I lost for firing at 15 degrees. Let's take a look at the 40 degrees. Now we're delaying up to 40. So if you take and you go 1 plus the cosine of 40 degrees divided by 2 pi times the peak of 170 volts. And at 40 degrees, you're going to see that we are now up to about 47.2 27.8 volts DC. This is the average voltage that we see across the load. Now, oh, sorry, I wrote that in the wrong spot. That is the 40 degrees. That's the 40 degrees. So the 40 degrees is 47.8 volts DC. Now, what about the 80 degrees? Now, this one has the most cut out of it, so we would expect that this would be the lower voltage. Now, how low could this get? Remember, we only have a resistance-only triggering circuit, so we can only actually trigger this SCR until 90 degrees. If we fired it at 90 degrees, it would be like getting half of that 54 volts. So if we had this circuit where we had 90 degrees, at 90 degrees, this would equal 27 volts DC. So we know that this 80 degree voltage needs to be lower than 47.8, but higher than 27. So it kind of gives you an idea where the boundaries are of the voltage. And so you should calculate this 80 degree angle out, and you should see about 31.8 volts DC. Now you could calculate that DC voltage at any one of those angles or fractions of angles. And so, you know, a real large process. You could do a whole bunch of practice on that. And but it's really just be careful using this formula and realize that the voltage you come up with had better be between, if it's a half-wave rectifier, it has to be somewhere between this 54 volts that you would get at 0 degrees, and if you're using a resistive only circuit, it can't be any lower than 27, because that's your last, the control of this circuit. This load voltage can either be off, you know, if you don't energize it, but as soon as you energize it, it can only be controlled somewhere between 54 and 27 volts DC. Okay, so that's your area of control voltage over this load. All right, what we're going to do is I want to take this circuit, and I know what you've been wondering is, okay, where does that trigger pulse come from? You know, we've been talking about the load voltage, all that kind of thing. How do we actually develop a trigger pulse, and how do we determine exactly when it will fire? So let's take a look. First of all, I've drawn a circuit. This is with a 120 volt supply, and I've put the load and the SCR in series. And in parallel, I've drawn the trigger circuit. So this line right here represents load circuit, and this over here is trigger circuit. Trigger circuit. And so the trigger circuit consists of a 0 to 15,000 ohm rheostat, and followed by a gate protection diode. Okay, and we talked about that. We need that to make sure that current doesn't try to flow the wrong way through the gate. And so that diode will protect that. Now we have some SCR data information here. This is a 30 amp SCR. It's I gate, so the current that it takes to fire it is 25 milliamps. And the voltage across the gate to cathode, the voltage drop when we're firing it will be about 1 volt. 1 volt across that. And really, this is a barrier voltage. I'm going to put here 1 volt. Now, we do have another voltage, a barrier voltage, and that's across this diode. And this is 0.7 of a volt. So if you add these two together, really, when we try to push current through here into the gate, we're going to have to overcome 1.7 volts of barrier voltage in order to be able to push the current in. Now, I want to show you what happens when you have a certain amount of resistance and you apply an AC voltage to it. It starts like this. As the voltage begins to rise across a resistor, to begin with, almost no current flows. Then, as the voltage gets higher, more and more current flows. And so as the waveform continues degrees at a time into its cycle, the voltage gets larger and the current gets larger and larger. Now these lines that I'm drawing represent current that would be flowing into the gate. So this current is literally current that would be flowing through here. Now, we know that this gate needs 25 milliamps. So what I'm going to show you is I want to show you this. Let's say that I set this rheostat for a value of 9,000 ohms, okay? 9,000 ohms. And so if you do a little bit of math, you're going to see that there must be an ultimate size or amount of current that can possibly flow in this circuit. And when will the highest, you're going to start with a very small current, and as the voltage rises, the current will get bigger and bigger and bigger. There is, however, an ultimate size to the current based on this resistor, these two barrier voltage drops, and the amount of peak voltage. So where's the highest current going to occur? Well, it's going to happen when you get to 90 degrees, because that's where the highest voltage will occur. So when we get to 90 degrees, what we want to do is we want to stop and take a little look. Okay, so now the current has been rising for 90 degrees, and bang, there we are. We're at the highest possible voltage. How much current do I have? So I go, well, how do I calculate this? This goes back sort of to an Ohm's law kind of a problem. And so let me see, how much current is that? I is E over R, right? Well, how much resistance do I have? 9,000 ohms. 9,000 ohms. And how much voltage do I have? Now, this can be a little bit tricky. What is the absolute peak amount of voltage? 169.7 volts. Do I have all of that voltage available just for pushing current? And the answer is no. So what you see is, yeah, we need voltage to push current, but we also have to overcome this 1.7 volts. And so what you need to do is you need to say 169.7 minus 1.7, and that equals 168 volts. So how much voltage actually is across this resistor that can actually push current? Well, it's 168 volts. So if we go 168 volts and we divide it by 9,000 ohms, let me just take a little check, and I'm going to go 168 divide 9,000, and I see that I have 18.7 milliamps. Now, this equals 18.7 milliamps. Now, how many milliamps do I need in order to fire the gate and turn this SCR on? Well, I need 25. So what's going to happen is this is not enough current to turn this on, so it will stay off. And moreover, the current's not going to go any higher than that. It's actually going to start going down again. So now the current starts going down from 18.7 and it starts to fall. It's still flowing into the gate, but it's getting smaller and smaller and smaller and smaller and smaller until the end of the alternation. That's the gate current we're talking about. Now, what do we have to do to successfully get 25 milliamps into here so we can fire this SCR? Well, we have to use a smaller resistance. And so what we want to do then is, if we started to lower the resistance, the current would actually start to rise faster. And so the first point, as we lower resistance, the very first point that this SCR will actually fire is when we get the resistance low enough to give us 25 milliamps at the peak. And so what we can actually do to find the resistance setting that we need to use is we can do this. We can say, well, what is the voltage, at the peak? 169.7. What is the barrier voltage? So we actually have that 168 volts, and we say, how are we going to figure out how much voltage, how much resistance, so R equals E 168, R is E over I, right? And what we know is that the current is 0.025 amps, because that's the amount of current that we need. So if we can get to this 90-degree point, we have 168 volts available to push current through here. We need 25 milliamps. And so if we size the resistor to give us this 25 milliamps when we have 168 volts, then we will successfully fire the SCR. And so what I want to do is I'm going to run this number through. It looks like 168 divide 0.025, and it's 6,720 ohms. So what I'm going to put here is 90 degrees, 6,720 ohms. And so we actually have to size this resistor. We have to tweak this dial until we have this value of current. And at that point, all of a sudden, the SCR will be fired at that point. And at that point, all of a sudden, we will start to have load voltage across this resistor. And the waveform of voltage will look like this. It will be blocking for 90 degrees, rising, conducting until the end of the alternation, and then it will be off for the negative alternation. So how much voltage will this give us across the load? It'll be E line times 0.225, because we only have 1/4 of what we would have in a full cycle. Okay, so that shows you the 90 degree. Now, I want to do a couple of more settings, and so let's take a look and see what amount of resistance would we have to use in this circuit to get a 60-degree firing angle, okay? 60 degrees. Now, how are we going to solve this? The question will always be, in order to find resistance, you need to know voltage divided by the required gate current. So let me show you. I'm going to use this space up here. We want to do 60 degrees. And the question is, how much resistance will give us a 60-degree firing angle? What you need to do first is you need to say, I'm going to look at my waveform here. I'm going to say, where does 60 degrees actually show up? And it's right about in here somewhere, right? 60, I would say about here. If I want a firing angle right here of 60 degrees, the first thing I need to know is, what is E instantaneous at 60 degrees? Now, does everybody out there remember what the formula is to calculate E instantaneous? I'm going to write it down here. E instantaneous is equal to E peak times the sine of the angle. And in this case, the angle is 60 degrees. So if we take 60 degrees, and I'm gonna use sine 60. So sine 60 equals 0.866. And I'm going to go 0.866 times the peak, which is 169.7. And my actual instantaneous voltage at 60 degrees, here it is, 140, and the decimals are so close, I'm going to call it 147 volts. That is the instantaneous voltage at 60 degrees. Now, is all of that voltage actually available to us to push current through the trigger circuit? And the answer is no, because we have to overcome barrier voltage. So that means we have to subtract 1.7 volts, which means I'm going to take away 1.7, and I have about 145.3 volts. 145.3 volts is now the voltage that I can use to calculate the resistance. So I'm going to use 145.3 volts. I'm going to divide that by this is IGT, which is 0.025 of an amp. And this will equal the resistance that I need. Okay, so let's go ahead and do that. 145.3 divide 0.025, and I'm looking at 5,810 ohms. 5,810, or very close to it. 5,810. So our first calculation that we did was, what is the resistance needed to fire at exactly 90 degrees? Now we've said, you know what, if we reduce this rheostat resistance to 5,810 ohms, then we're actually going to get a 60-degree firing angle. Now for the load, what is that going to look like? Well, it's going to look like this. Okay, so this one here is at 90 degrees. Let's look at 60 degrees. Well, let me just show you a dotted waveform like this, okay? We know that it's going to block over here. So at 60 degrees, that means we're going to be blocking, 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 blocking. Now at 60 degrees, we're going to, at our firing angle, it's going to rise up to here. We're going to see a little bit. In 30 degrees, we're going to rise a little bit more, and then we're going to fall until the end of the alternation. So will this voltage be more or less than this voltage? This one is 60 degrees. Okay, remember, just think of these as blocks of ice that you have to melt down to water. The water is actually your average voltage. This block of ice melted down will be less voltage than this block of ice melted down. And so you can always think of it that way. The average voltage will just be the result of taking this total mass of area and saying how much is it as a percentage of the whole rectangle. So at 60 degrees, we're earlier than 90 degrees. And remember what I said, later firing is less voltage for the load. So this is later firing than this. That means this is less load voltage than this. Okay, the last thing I want to do, I'm going to kind of summarize now a little bit. And many of you recall seeing these kind of things. I used to have them at country fairs and here and there. I'm sure you've seen them, or if you haven't seen one, you're at least aware of how they work. You have to pay to play. You basically pay your fee. You come in, you grab the sledgehammer, you hit the pad down here, develops air pressure. The ball goes up, and hopefully it rings the bell at the top. If it doesn't ring the bell, it just falls down. Then you have to pay again, right? So you can play again. So if you get to actually hit it hard enough that it goes up and rings the bell, you win. Now we can compare this a little bit. It's a kind of a similar idea when you have a resistance only trigger circuit. And here's the way that it's similar. You set your resistor, okay? You set your resistor, you have an ultimate level of peak voltage, and what happens is your current, your voltage waveform starts to go up and your current starts to rise. And it goes up, it goes higher and higher and higher. And finally, it gets to the top. If it is not enough current to ring the bell, or in our case, to fire the SCR, then the SCR is going to remain unfired. In other words, it will still be open, and the current during the second half of this 180 degrees is just going to fall. And you won't get another chance. You won't get another chance to try even until after the negative alternation has gone by, and then you start on the next cycle, and the voltage will start to go up again. Now, if you don't change the resistance in between here, all that happens is your current will keep going up to a maximum value and back down, dead space, up to a maximum value and back down, another dead space. And so you don't fire the SCR, you don't ring the bell, doesn't work. And so if you fire by 90 degrees, then you have success, okay? Now the rest of these pulses will still enter the gate, but as long as you actually fire by here, then your SCR will give you voltage. You know, it'll be closed and the load will have voltage from 90 to 180 degrees. You will have load voltage. Now, your option is to reduce the resistance, and that way you'll hit your firing current level sooner and sooner and sooner and sooner. And if you lower your resistance low enough, you can virtually fire, you know, all the way to 0 degrees. Now, practically speaking, I want you to remember that there was 0 degrees, which was about 54 volts, and 15 degrees was the angle that I showed you. And the voltage at 15 degrees was actually 53.2 volts. So you only lost about 0.8 of a volt for having 15 degrees. And so we don't worry much about trying to make trigger circuits that come earlier than 15 degrees, because that's just simply not enough voltage to make a difference. So the idea is, with a resistance only, we want to basically be able to fire the SCR at some angle, and the latest angle that we'll be able to fire it at is 90 degrees. And if we don't fire it by 90 degrees, then the SCR is just going to remain off, like a completely open switch, and we'll have actually no voltage there at all. Now, the best way to proceed with this is that we need to do some examples. I want to do some examples for you, and we'll work them out on the board. You'll be able to watch how I look at them and where I put the voltages and the currents, and we'll work our way through them. So I'm probably going to do 3 or 4 examples, and so we're going to go to that just next.